Heat is, well, it's everywhere, isn't it? You feel it from the sun, you use it to cook, you even feel it leaving your body on a chilly day. But have you ever stopped to think about what's actually happening? Like, how does heat get from point A to point B? Well, that's exactly what we're going to dive into, this incredible, fundamental force that pretty much shapes our entire world.
Okay, think about this. We've all done it a million times, right? You put a pot of water on the stove, you crank up the heat, and you wait. But what is really going on there, down at the molecular level? How does the energy from that flame actually get into the water and make it boil? It turns out this super simple, everyday act holds all the secrets to understanding heat transfer.
All right, before we get into the nitty-gritty, you need to know the one single unbreakable rule of the game. And it's this: heat always, and I mean always, flows from hot to cold. That's it. It's a fundamental law of the universe. You can think of it like nature is constantly trying to find balance, to even things out. Scientists call this thermal equilibrium. And if you can just lock this one idea in your head, everything else is going to make so much more sense.
Okay, so if heat is always trying to move from hot to cold, the big question is, how does it actually make that trip? Well, it turns out there are three main ways it gets the job done. You can think of them as the three main characters in our story: conduction, convection, and radiation. And here's the cool part. These three processes are rarely flying solo. In the real world, they're almost always working together, like a team. Just look at this kettle, for example. You've got the flame radiating heat, the metal pot conducting that heat, and the water inside is swirling around or convecting. It's all happening at once. So let's break each one down. So first up, we've got conduction. This is basically heat transfer through direct contact, literally by touch. Imagine the molecules at the bottom of that pot getting super hot and vibrating like crazy. They start bumping into their neighbors, which makes them start vibrating, and so on and so on. It's like a microscopic chain reaction, passing energy right up the line. And in our kettle, that's exactly how heat travels from the hot base all the way up through the metal handle. Okay, next up is convection. Now, this one only happens in fluids, so we're talking liquids and gases. You know the old saying, hot air rises? Well, it's the same for water. When you heat the water at the bottom of the kettle, it expands, gets a little lighter or less dense, and floats up. Then the cooler, heavier water from the top sinks down to take its place, gets heated, and rises too. This creates this awesome circulating current that efficiently moves heat all through the pot. It's heat transfer by the actual movement of the fluid. And our third and final character is radiation. Now this one is really special because it doesn't need anything to travel through. No molecules, no direct contact, nothing. Heat is transferred as electromagnetic waves, kind of like light or radio waves. This is how you can feel the heat from a campfire, even from a distance. And the big one, this is exactly how the sun's heat gets to us through the total vacuum of space. Okay, so here's a quick cheat sheet for you. The absolute biggest difference to remember is the medium. Conduction and convection both need stuff, solids, liquids, or gases, to travel through. But radiation? That's the rebel. It can go right through empty space, no problem. And this totally affects their speed. Conduction is the slow and steady one, passing energy from one molecule to the next. Radiation, on the other hand, is the speed demon, traveling at the speed of light. Okay, so now we know the three ways heat can move. But that's really only half the story, right? The next obvious question is, how fast does it move? What are the things that control how quickly that energy gets from one place to another? Let's just use our intuition here for a second. Imagine you take a frozen pizza out of your freezer and just leave it on the counter. Heat will slowly start to flow into it, right? But now, imagine taking that same frozen pizza and putting it into a blazing hot oven. Bam! The heat flows into it way, way faster. It's pretty simple. A bigger temperature difference creates a much stronger push for that energy to move, speeding the whole process way up. Okay, now for another gut check. What about the path that heat has to travel through? Think about it. Wearing a thin little windbreaker versus a big, thick, puffy winter coat. Which one's going to keep you warmer? The thick coat, obviously. And that's because more material means a longer, tougher road for your body heat to travel before it can escape. So let's kind of pull all that together. The speed of heat transfer really boils down to four key things. We've already talked about the temperature difference and the thickness of the material, but the area also matters a ton. Think about how a giant radiator has a huge surface area to pump out heat compared to a tiny one. And of course, the material itself is absolutely critical.
There's a reason we cook with thin metal pans to get heat in fast, but drink coffee from a thick ceramic mug to keep heat in longer. It's all about controlling these variables.
All right, now here's a really cool trick that engineers use all the time, especially when they're dealing with complex problems. They borrow an idea from a totally different field, electrical circuits. It sounds kind of weird, I know, but using this analogy is an incredibly powerful way to actually visualize and solve how heat is flowing through things. Here's how the analogy breaks down, and it's surprisingly simple. The temperature difference, that's just like voltage. It's the pressure that's pushing everything along. The rate of heat flow, how fast the heat is moving, that's basically the current. And finally, any material that slows down heat, like insulation, that's your thermal resistance, which is exactly like an electrical resistor in a circuit.
And this is exactly why this analogy is so powerful. It helps us figure out how heat moves through complicated layered stuff, like the wall of your house. You've got drywall, insulation, maybe some wood studs. Are those layers stacked one after another, like resistors in series? Or are they side by side, like the studs next to the insulation, which would be in parallel? Thinking about it like a circuit gives us a clear blueprint to figure it all out.
Okay, so we've covered the what's, the how, and the how fast. Now for the fun part. Let's connect all this back to the world around us. Because I promise you, once you know what to look for, you're going to see heat transfer in action absolutely everywhere. All right, let's start with the classic one. Picture this. You've got a metal spoon and a wooden spoon sitting on your kitchen counter. They've been there all day, so they're both at the exact same room temperature. So why does the metal one feel so much colder when you pick it up? Well, the answer is all about conduction. Metal is a fantastic thermal conductor, while wood, not so much. The spoon isn't actually colder. What's happening is that the metal is just yanking the heat out of your hand incredibly fast. And it's that rapid loss of heat that your brain interprets as the feeling of cold. Okay, next puzzle. We all know that the space between the sun and the earth is a vast, empty vacuum. There's pretty much nothing there. So how on earth does the sun's heat make it all the way to us? Of course it can. And the hero of this story, as you've probably guessed, is radiation. Remember, it's the one that doesn't need any stuff to travel through. So the sun's incredible energy just radiates out as electromagnetic waves, traveling across 93 million miles of empty space to get here and warm our planet. Pretty amazing, right? Without it, we wouldn't even be here. And honestly, the applications are just endless. Once you get this stuff, you see it everywhere. It's in the insulation in our homes. It's why we choose certain pots and pans for cooking. It's how convection ovens cook our foods so evenly. Heck, it's even behind global ocean currents and weather patterns. Even something as simple as roasting a chicken is a total masterclass in heat transfer. You've got radiation from the oven coils, convection from the hot air, and conduction right into the chicken itself. See, heat transfer isn't just some boring topic in a science textbook. It's this living, breathing process that's happening all around us all the time. The heat coming off your laptop, the sunlight streaming through your window, the way your drink is slowly getting warmer or colder. So, now that you know the rules of the game, I have a final question for you. Just take a look around. How is heat moving around you right now?